I was wrong, Catherine. You were right. Thank you very much. I do appreciate it. All right.
Professor, how come I'm getting a different number?
If you do this, 36 minus 7 divided by 6, you for sure will get the wrong answer. Because here's what the computer is seeing. Did you get this number?
No.
No. What did you get?
I got 14.5, I think it was.
Okay. So let's try it again. So just 36 minus 7 equals. Then divide by 6.
Yeah, okay. I must have put, I'm getting it now for some reason. Yeah. Sorry about that.
That's okay. Yeah, that's the thing with these machines here. If it's wrong, it's 100% user error. So I get students that are like, my calculator's not working. No, it's working just fine. It's just not being improved. So that's why I want you guys to practice. So exactly like with what happened with Michael, that if he does make a mistake, we can figure out how to fix that. Okay. So let's use purple. I'm going to do all of this, but what I'm going to do is I'm going to make a big table right here. So we're going to make our frequency distribution table now. On one side, I'm going to have the height. And I'm going to start with the smallest number. In this case, that's 7. Now, if you remember, the classes are going to be a class width apart for the lower boundaries, the lower class limits. So to get the next lower class limit, I'm going to add 5. To get the next one, I'm going to add 5.
I have a question.
Yes, ma'am.
So you started off with the minimum, right? Which
Correct.
is 7.
That's right.
And then you just adding 5 to those. Okay.
Yeah.
Thank you.
It feels almost too simple.
And then you put 6 classes because obviously in the sentence it says there's 6, right? Okay.
Now, in real life, of course, you would decide how many classes you want to have. What number of classes is going to work best to communicate whatever it is you're trying to communicate with the data.
Okay.
Yeah, too few is not going to be useful. Too many, it's going to be too chaotic.
Right. Okay. Thank you.
Got it. All right. Now we need our upper class limits. Sean asked if it's going to be exactly 5. It's exactly 5 because I calculated it here for this particular set of data. So a different set of data may have a different class width, which will mean I'm going to have to use something else. For example, in the previous set of data, the class width was 20. So plus 20, plus 20, plus 20, plus 20. Now, the upper class boundary, class limits are going to be, so if this lower here is 12, less than that's going to be 11. One less of that, it's going to be 16.
Here when you use a new one.
Oh, 1 second, guys. My wife has a question. All right, I'm back. And I see stuff in the chat room. Ah, got it. Glad I could clarify, Sean. All right, so again, one less, and so on. Now notice my upper class boundary limits, I'm also adding 5, plus 5, plus 5, plus 5. Now I don't have another one here to tell me what goes there, but again, I could add 5 if I need to, 36. Plus 5, plus 5, plus 5, plus 5, plus 5, and so on. And any questions on where I got these numbers from?
Yes. Where'd you get the 11 from?
So if the next one is 12, that means the previous one is going to be in the previous class. So one less than 12 is there. One less, and so on.
Okay, got you. Thank you.
You got it. All right, let's talk frequency. I'm going to go back to my table, stat, edit. And here's my table. I don't think I can write that, but that's okay. So how many of these heights are between 7 and 11? 7 is between there, and 10 is between there, so 2. So my calculator's in the way. It's hard to write. Let's do this. Let's move this over here. And that's better. How many data values are between 12 and 16? Well, I have 12, so 1, 2, 3, 4, 5. 5 of them are. How about between 17 and 21? 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's bigger than 21, so 9. Do you see why organizing it like this, putting it from smallest to biggest, makes it easier to fill in the table? So between 22 and 26, 1, 2, 2. And between 27 and 31, there are none. It jumps from 24 to 36. And between 32 and 36, there's only one value. How are we doing? All right, we are moving on. We have other types of frequency distributions. We have a relative. Frequency distribution. Sometimes called a percent frequency. And this is the same data from before, so I'm going to go ahead and fill this in. This is 2, 33, 35, 7 and 1. It's the same table here. It's the same one from page 1. So these two tables are the same. And I'm going to add another table here. Now I'm going to need to know the total, meaning this total, when I add them up. So 2 plus 33 plus 35 plus 7 plus 1, 78. And here's how we do this. I'm going to take the first class here, and I'm going to take the 2 and divide it by the 78. And that's going to be my percent. Right? To change the decimal to a percent, you got to move the decimal over twice, right? Or times 100. For class 2, I'm going to use 33. And so on. Now, ideally, if I were to add up all these percentages, I should end up with 100%. Now, due to round off error, that could be off a little. Easy enough? Not too bad. Next up, we have a cumulative frequency distribution. If you don't know the word cumulative, it means the sum of everything before it. So for example, your final exam will be cumulative, meaning it's not just gonna be on the last chapter, it's gonna be on all the previous chapters as well. And you'll notice that the scores are listed a little differently than the previous ones. Here we had a range, and here we don't. Now, this is in here. We had range, and here we don't. It's less than 70. So how many of these data pieces are less than 70? Less than 70, there's only 2. How about less than 90? Here's 90. How many are less than 90? Well, that's going to be 33 plus 2, which is 35. How many are less than 110? Well, that's going to be 35 plus 33 plus 2, all the previous ones here. Less than 130? Well, that's going to be 7 plus 35 plus 33 plus 2. And the last category should have all of the numbers of data. Yes, I can, Sean. The graph for this one is really cool. It has a cool name. It's called an ogive. You know anything with the word jive and it's got to be cool. It's spelled with a G though. Ogive is what it looks like. All right, I have a request from a student who wants to go back a little bit to the percent one. Sean, if you want to unmute yourself, please ask. How can I help you?
Well, yeah, I just needed to copy it down
Okay,
again.
no problem.
I missed some stuff.
No problem. Let me give you guys another minute to finish copying. I'll be right back. All right. How are we doing with all this? All right, let's move on to the normal distribution. Now, I want to point out, once again, as I mentioned before, you can see all of the big data is in the middle in this case, and then it kind of peters off. We call this a normal distribution. And this is sometimes referred to as a bell curve because it looks like an upside down bell. And eventually we'll be very interested in how much area is underneath this curve. So this whole idea of the vast majority of the data or information is going to be in the middle. You can picture heights of people. So if I found the average height in our class, Most of you would probably be pretty close to that height. There might be someone considerably smaller or considerably larger. All right. We're on to histograms. A histogram is a graph consisting of bars of equal width drawn adjacent to each other. It's kind of looks like a big black blob here, but you can see there's 1, 2, 3, 4 classes, 5 classes in this case. We include this last one. This is the IQ data that we've been using today. And there is a relative one as well.
Does this have any correlation with histology?
Histology? I don't know. I don't know what histology is. Perhaps it is very likely connected to it. I don't know.
Okay.
Yeah, look into it. Let me know. Teach me something. Now, again, you can see the vast majority of the data is in the middle. You can almost see a nice bell curve there as we're looking at that. It's rough, but it's there. This is a regular histogram. This is a relative. It's hard to see, but these are decimals as far as like percents go. And so this one would represent this relative frequency distribution. And you can see if we break it up even more, we can really see the bell curve there. Now this is called a uniform distribution. These ones are boring as far as from a mathematical point of view. This just means that everything is equally likely. And last up on this page is when we have a longer tail. This side is the longer tail. You can see the longer tail. Again, here you can see the longer tail. We see that it's skewed. Longer tail's on the right. Longer tail here's on the left. Yep. So a distribution is skewed if it's not symmetric. Symmetric means it's equal from one side to the other. For example, people tend to be symmetric, right? Chop them right down the middle. No one is perfectly symmetric. And the data is skewed right. If there's a longer right tail, and it's skewed left. If it has a longer left tail. It's not bad if data is skewed. That just means we need to look into it a little more. And now we're going to have a bunch of different types of graphs. I'm going to go through this a little bit quickly because it's not particularly difficult. And I want to get to chapter 3 at least a little bit. This first one is called a scatter plot. Ohayou gozaimasu. A scatter plot is just a regular graph. So for example, this right here represents the point -1, -3. -1, -3. Just like you've always done like in your algebra class. Right, an ordered pair. The next one would be -4, -6. I'm not going to take the time to put them all on there, but you can see that we're just plotting the points. And later in the semester, we'll learn that if we can start seeing some pattern with all these points, then we can start making some predictions with them. And so I want to move on to the next one. This is called a dot plot. Consists of a graph in which each data is plotted as a point along a horizontal scale. I'll show you what I mean here. So here we have some data. And what I'm going to do is I'm going to rewrite all of the numbers in so we can make it clear. So this is 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, and 45. Sorry if that's a little messy. So for 38, 38 is right here. So I'm going to put a dot. 39 is here. 37 is here. 37 again, it's going to go above it. 44. 38 again. 41. 38. 39. 35. 42. 39. 43. 43. 37. And 41. I missed a 38. There it is. And you can almost see a skewed bell curve. Do you see it where we have a longer right tail, a skewed right?
There's no 40 though, right?
There isn't, and I don't know why there's one there. So there, that just makes it look like there really is a 40, but I meant to scratch that out. But you're right, there's no 40. This is showing how bad my vision is. I need glasses, I'm getting old. All right, next up, we have a stem plot. And I'm going to give you a minute. Would you please enter this? I put this data into, I think I put it into list 2. Yeah. So go ahead and take a minute. You can clear list 1 if you want, and copy over that, or you can put it into list 2, which is fine. So I'll give you a minute to put all that data into list 2. And then I want you to sort it as well, so that it goes from smaller number to bigger number. See if you remember how to do that. If you remember how to sort it, you go to stat and then sort ascending order. And I put mine into list 2. So if you remember, I have to hit the blue first, and L2 is above 2. So second L2. And that should put it in order, which it does. And I put it from the smallest to the biggest, and I want to notice that the largest value is a 20, and the smallest, I'm going to go up, and it's going to drop it down to the bottom of the list. And the largest is a 65. So here's how I'm going to do this. Smallest is 20, largest is 65, and then we got stuff in between. So here's how this works. And I'm now going to go by my list. How many 20s are there? So I have a 20, a 20, a 20, a 22, 23, a 24, a 24, a 25, 27, 28. And that's it for the 20s. Next up, I have a 30, 32, 35, 37. And I have a 41, a 42, a 47, a 48, a 49, a 50, a 52, a 58, a 60, and a 65. You guys see how I'm doing that? And why it's nice to put it in order like that? Everything's kind of right there for you. Now, I had a teacher, I think in junior high, she put all of our test scores, after we took a test, she put all of them up on the board like this. And this way I could figure out where I stood relative to the rest of the class, and no one knew what score I had. So I know that if I scored a 47, I did okay. Not too bad. Most people did not as good as me. If I got a 20, I know I'm at the bottom of the heap. I didn't do so well. If I got the 65, that means I got top score in the class. Now you can imagine, I teach a couple of stat classes, as I mentioned. You can imagine I give a test to you guys and they give the same test to a different class. And if I want to compare the two, what I can do is I can actually draw another line here and have a double one. And I can directly compare the two classes to see which class did better, and maybe ask myself, why did one class do better than another, and so on. All right, moving on. These last few are not, I'm not going to spend a lot of time on them. Yeah. This first one's called a multiple bar graph. And you can see this is directly comparing two different things. You could compare 3 or 4 different things if you needed to. This one in particular is income by gender. And actually, that's a little out of date. It should be income by sex, but that's fine. And you can see traditionally men make more than women. As much as men try to deny that, that's unfortunately the way it is. Next up, we have called a Pareto. I'm pretty sure that's someone's name. And it's a bar graph that shows by decreasing frequencies. So what contributes most to happiness? Family or your partner? And then I think it's friends, leisure, work or studies, and so on. The last one is the pie chart. And let me define this a little better. Oh, you guys can't see. When I do that, you guys have to tell me to push the paper up, please. Someone be brave, just let me know. I'm better at it now than I used to be, but by the way, these two are the same data, right? Family and partner, the largest chunk. This is originally in color, and you can see the nice bright colors, but black and white, it just kind of turns out to be a big black blob. This last graph is a little more interesting. This is called a frequency polygon. And we are back to our table. This is the same IQ table that we've been using all day. And what we're taking are the class midpoints. We did that at the beginning. Class midpoints, if you remember, you add up the two, divide by 2 to get the class midpoint. And there's our 59.5 there. So the class midpoint is going to be represented here with a 2. This next one is 79.5. That's going to be up here at 33. This one's at 35, just a little higher. This one here is down to 7. This one down here is at 1. So here's how this works. There's our frequency polygon. Let me just give you a minute to finish copying that down. And again, this very nicely gives us that we can see most of the data is in the middle. And lastly, how we can use graphs to trick people. Now, this graph is about car efficiency, gas mileage. And you can see it looks like the Honda Civic blows the Toyota Camry out of the water. Like there's absolutely no contest between the two. And the Chevy Aveo is in the middle. However, I want to point out these two graphs are actually the exact same graph. And in reality, these three are very close to one another. But what someone did was they took this graph and they chopped it off at 30. To make it look like this. Do you see how this looks way worse than that? Fox News does this. Just be on the lookout. Pay attention. Now, it is labeled properly. If you really want to deceive, then you don't put the label on properly. That's really trying to trick someone. All right. I'm going to skip these for now. No. Yeah, we just need to move on. Okay. I want to start chapter 3. Where did chapter 3 end up? Yeah. Okay. Sorry, guys, give me one sec.
What's the chapter?
Chapter 2. This
This is
what I was writing on, and this is what I was using as notes.
the chapter 2. Keep it.
And we'll see how far we can get in 20 minutes. All right, so chapter 3, we're going to start by measures of center. Okay. Measures of center. Is how do we find the middle of a data set? And there's a bunch of different ways to do this. In fact, we have a whole page that we're going to do this with. Hands down, the most common is what's referred to as the mean, sometimes called the average. The problem is average often refers to a general measure of center. The mean is very specific. And we're going to learn a new symbol today. This is the sum of the data. This weird symbol that's new for us is called a sigma. It's a capital Greek letter S. And if it's a sample, we use the symbol X bar. If it's the entire population, we use the Greek letter mu. We talked about that last time. It's a lowercase m in the Greek alphabet.
Is that what's next to the mean on the top
Next,
in black?
you mean here? No.
Yes.
That's a accidentally I wrote in black and I meant to write it in purple. All right, so we're going to find the mean of a data set. So we're here, and to find this mean, I'm going to add up the data, 22 plus 22 plus 26 plus 24 plus 23. And there are 1, 2, 3, 4, 5 pieces of data. And if I had more time, I would do these with you as well, but we don't. So we're gonna move on to the next definition, which is the median. And the median is the middle number. Now, what we need to do, first off, is rewrite the data set in order. So you could put it in your calculator and hit sort. I'm gonna do this one by hand. Now, here's how we find the median. I start on the outside and I go in one and I keep going until I come to the middle. 23 is the median in this data set. I'm going to add a data set, a datum to this next one. And I'm going to reorganize it in order. So I'm going to do the same thing I did before. I'm going to start on the outside. I'm going to go in one. I'm going to go in one. I'm going to go in one. And I'm going to note that there's not a single number in the middle, but in this case, there are two. What do we do when there's two in the middle? We find their mean. How are we doing? Cool. Next up, we have the mode. The mode is the most frequently seen data value. In this case, 22 is repeated. So the mode in this case is 22. In this case, there are several modes: 22, 23, and 26. We would call this trimodal. If there are two, we would call it bimodal, right? Bi means two. All right. Now this last one, there are no repeats. So we would say that there's no mode. Some textbooks would say that all of these are the mode because they're all repeated one time. but your textbook says no mode. Now, to be clear, why you would use the mode, let's say you had a store and you had 50 items that you sell and you number them 1 through 50, and you notice that item number 27 is a really hot seller. Well, that's going to be your mode. You're going to be like, hey, that 27 is coming up a lot. I better advertise and let the whole world know that I've got item number 27 for sale in my place so that they come and get it type thing. And even numbers that aren't the mode, so maybe 27 was repeated the most, but item 13 had quite a few, and item number 47 also had quite a few. Well, let's advertise for those as well. All right, next up. Mid-range is just basically, it's the biggest and smallest number in the data set and finding their average. So it's the max plus the min divided by 2. And so if we find the mid-range of this here, it's going to be the max, which is 26, plus the min, which is 22, divided by 2. And I want to point out that I have the same data set as the first data set for all of these different ones. So for the mean up here, I got 23.4 as a measure of center. For the median, it was 23. For the mode, it was 22. And for the mid-range, it's 24. So you can see they're all pretty close to one another. Each one sort of tells its own story. It gives you data that you're interested in. This next one takes a little bit longer. Now, if we want to find a mean for a frequency distribution table, meaning we don't have the raw data like we had up here, then we're going to have to do something else. What we're going to do is we're going to find the class midpoint. If you remember, the class midpoint is, this is that same IQ data set that we have been using all day. The midpoint was going to be the 50 plus the 69 divided by 2, which gives us the 59 and a half. This one's 79 and a half, 99 and a half, 119 and a half, and 139 and a half. Again, I'm adding the upper and the lower limits, dividing by 2. And the way we find the mean so here's my sigma notation again. What's going to go right here is adding up the frequencies. We did that earlier, that was 78. Now this column is going to have f times x. So 2 times 59 and a half is 119. 33 times 79.5 and so on. I'm going to have you fill that in. And then when you're done, I want you to add up all of these because what's going to go right here is my numerator. I'll give you a few minutes to do that. All right. Once again, please double check my numbers.
Can you just scoot the paper up a little bit, please? Thank you.
You guys are so picky. We want to see what you're writing. Now, this is just an approximation of the mean, because we're assuming that all of the data that's here is exactly the class midpoints, and that's just not true. And as we're running out of time here, there's at least one thing I want to show you. We have 14 minutes, yeah. I gotta do standard deviation first. Yeah. All right. Here now measures of variation. All right, we're gonna start with the range. The range is the max minus the minimum. For example, with this example, the max in this case is 26, the minimum is 22. And our best measure of variation is not necessarily the range, it is what's called the standard deviation. And I want to talk about that for a second, kind of explain what that is. For a sample, we use a capital letter S for the standard deviation. The formula, which we won't use, your calculator will do all of this for us. So we're adding up the difference between a datum, and the mean, squaring it divided by n minus 1. some properties. The standard deviation is the measure of how much values deviate away from the mean. And let me give you an idea of what standard deviation, what exactly the meaning of that is. So let's say that I give a test for this class and the average score, the mean score is 70%. A small standard deviation would mean that the scores, the mean is 70%, the scores are 71, 68, 72, 70, 69. They're all very, very close to the mean. A large standard deviation would mean that the mean is 70, but someone got a 95, someone else got a 2, someone else got a 7, someone else got a 100%. So you can see the distance from the mean is really far. That's a large standard deviation. So the standard deviation is basically the average distance from the mean, the middle part, if that makes sense. The value of the standard deviation is, I want us to correct this. This is not usually, it is always positive. And those of you who remember your algebra, you know that when you take the radical of something, it's always going to end up being positive with real numbers. The units on a standard deviation are the same as the original data value. So for example, if I'm wanting to find the standard deviation of the average heights in my class, in this class, if I'm measuring you in inches, that means that the mean will also be in inches and the standard deviation is also in inches. So they're all the same unit. And the last part is that this is a biased estimator. Of the population standard deviation, meaning it's not going to be the same as the population standard deviation. It's biased to whatever data set I found that and was using that to project into the population. All right. Okay, so we're getting there. So I'm going to go ahead and put this data into list 3, which I did earlier today. So that's this data here. I want everybody to do this. So let me give you a minute to put those 5 pieces of data into, I put it into list 3. You can clear your list 1 and put it into there if you want. You can do whatever you'd like. I'm not done yet, but I'm not going to be able to finish all of chapter 3. So you can watch the video that I already have in Canvas for you that goes through exactly the same sheet and everything. And it's me talking. It shows you calculator. Okay, so now I've put that in there. I could use this formula to do it by hand, but why bother? The calculator will do it for me. I'm going to remember I'm in list 3 here. So I'm going to quit out of that. And this is very, very important. You'll want to write this down. One var stats. So I'm going to go to stat and calculate. And there's my 1 var stats, 1 variable statistics. It wants to know what list I want to do this to. I put mine in list 3. That's going to be, my list 3 is above my 3. So it's second L3. There's no frequency list. And I hit enter. Now, we found the mean to this earlier. There it is, X bar, 23.4. If you look back in your notes, it's the same. 23.4. But it does the standard deviation for you, and that is the S. 1.67332. Isn't that nice? It does everything for you.
Can you do that one more time, please? The 1 var stats on the calculator.
I can. You hit stat.
Stat. Okay.
Calculate.
Okay. Oh, okay.
Put in the correct list and calculate. Now, as I'm definitely running out of time, I want to point out that for a different part of the lesson, we run into something called percentiles, and more importantly, quartiles. And to find these quartiles, I want to show you, we just did. I can scroll down. There's my minimum, Q1, Q2, Q3, and my max. So you may want to write down the word quartile with the one variable stats. That's going to get you those values automatically. You need to see the word quartile. Let me just show you here. Right there, quartiles. And so the 5 values that we just saw were here: 1, 2, 3, 4, 5. The min, Q1, Q2, which is the median, Q3, and the max. One last thing I'd like to show you is when we go 2 standard deviations away from the mean, we're going to capture 95% of the data. Here we are 2 standard deviations away. 1, 2, 1, 2. 1 standard deviation away, we capture 68%, 95%. And if we go 3 standard deviations away from the mean, we're at 99.7%. But this is what is called is usual, versus more than 2 standard deviations is going to be unusual. And when I say unusual, when we're talking about people, I'm not saying that the people are unusual, but someone could be unusually tall. That doesn't mean that there's anything wrong with them, or unusually small. Again, that doesn't mean that there's anything wrong. It's just our way of saying the vast majority of chocolate chip cookies in a cookie are going to be 2 standard deviations away. If there's more than 2 standard deviations or less than 2 standard deviations, it's considered unusual. And that is going to have to be it for today, you guys. Please watch the other videos to finish this. Thanks, everybody.
One quick question. Can I just see the bottom of page 1?
Bottom of page 1.
Yes, sir.
And I'll stay after if anybody else has any questions, but other than that, there won't be any more new information. So class is considered
Thank
over.
you.
You're welcome. Thank you, everybody, for coming. Those of you showing your lovely faces, I do appreciate it as well. Thanks for the nice words in the chat.
Awesome. Thank you.
You're welcome. Take care.
Professor, I have a question. The videos, can we find them on Canvas?
Yes.
Or okay. And are they these that you're recording, or previous ones?
Yeah, it's me recording myself.
Okay.
Doing exactly this. Yeah.
All right. Thank you. I appreciate it.
You're welcome. Take care.